So far, we've talked about the fact that both neurons and muscle cells have this property called conductivity. We said that all cells have a resting membrane potential, which is essentially just a gradient of charge, a difference in charge between the inside and the outside of the cell, with the inside of the cell being relatively more negative than the outside of the cell. And if we measure that negativity, it comes in at about minus 60 millivolts. We said that cells that have the property of conductivity, again, neurons and muscle fibers, those cells have the ability to put resting membrane potential into motion. What we're going to do now is talk about how these cells are able to put membrane potential into motion along the length of their membrane and thus generate electrical current. Remember, when we talk about a nerve signal or a nerve impulse, what we're talking about literally is electrical current. What we need to understand next is how. How does a neuron generate electrical current? How does a neuron send membrane potential, again, a charge gradient, down the length of its membrane? And the answer is through differential opening and closing of sodium channels and potassium channels. Remember, at rest, the neuron and all cells are relatively more negative inside than they are outside. By opening and closing sodium and potassium channels, the neuron is going to be able to rapidly change resting membrane potential into other states. And by opening and closing those sodium and potassium channels in sequence along the length of the membrane, the neuron can generate electrical current. So let's think about some of the states that can be generated inside a neuron other than resting membrane potential. On this slide, I have resting membrane potential abbreviated as RMP. RMP can change very suddenly because of the presence of ion channels in the membrane. When an ion channel is opened, ions are going to flow, remember, down their concentration gradient. And they're going to do so rapidly and until either the channel closes or equilibrium is reached. So it's the changing concentrations of ions as they pass through these ion channels that will change the relative membrane potential, moving it away from that minus 60 resting state. If the inside of a neuron suddenly becomes much more negative, we're going to give that a name. We're going to call that hyperpolarization. If the inside of the neuron suddenly becomes much less negative, we're going to give that a name too. We're going to call that depolarization. Now, I'm using these phrases more negative and less negative, but I want you to remember something. If the inside of a cell becomes more negative, it's also becoming less positive. If the inside of a cell is becoming less negative, that means it's also becoming more positive. We need to remember all four of those phrases as we talk through the generation of electrical current. It's sodium channels and potassium channels that are doing this important work of generating electrical current in neurons. We have to remember that sodium is normally higher outside the cell than inside. So when sodium channels open, sodium is going to rush into the cell, down its gradient. That's going to make the inside of the cell suddenly more positive, or remember, less negative, and that's what we call depolarization. Now, the potassium gradient is essentially the opposite. At rest, there's more potassium inside a cell than there is outside. So when potassium channels open, potassium is going to rush out of the cell. It's going to take its positive charge with it. So that's going to make the inside of the cell less positive or more negative. And that's the state that we call hyperpolarization. If you can learn this information right here in the bottom half of this slide, you'll be well on your way to understanding generation of electrical current. So the question is, when and why do these ion channels suddenly open up? What causes them to open and what causes them to close? And the answer is electrical current, electrical signal coming from another neuron or another cell. In other words, these ion channels are voltage gated. They're gated, remember, and what we mean by that is they're not just open tunnels. They have a gate across one side, essentially. It's actually tucked into the ion channel. That gate is closed unless a certain voltage is hit at the membrane. When a certain voltage is reached, it's going to cause the gate to open. All that gate is a piece of the protein. Ion channels are membrane proteins, and a piece of that protein juts out and essentially closes the passageway in the channel. When a certain voltage is reached, the voltage is going to cause that gate to change shape and essentially swing out of the way, opening up the channel. When that voltage is reached, and the gate opens, it's only going to stay open until another particular voltage is reached, and that voltage will cause it to close again. So these are voltage-gated channels, and it's voltage that determines when they are open and when they are closed. What nerve cells, what neurons are capable of doing is opening up sodium and potassium channels differentially, in other words, at different moments in time and in different locations. And that's going to allow the depolarization and the hyperpolarization to essentially occur at different locations across time. That is putting charge gradient, putting electrical current into motion. That is what we call an action potential. Over the next several slides, we're going to look at a graph of electrical potential across the membrane of a neuron. We're going to apply a stimulus to a neuron, and we're going to see what happens to the voltage across the membrane again. And we're also going to watch what happens specifically at the sodium channels. Now, the potassium channels are also involved in this, but they're not drawn on this particular slide. So up at the top, what we're looking at is a graph that shows time on the x-axis, and this is in milliseconds. And on the y-axis, we're looking at membrane potential in millivolts. All this upper graph is there for is to show us when the stimulus is received by this neuron. The middle graph here has the same axes, time across the x-axis, again in milliseconds, and voltage on the y-axis. And you can see the voltage is ranging from approximately minus 60 all the way up to about plus 50. And you can see this pink line here changes across these 2 milliseconds. The green line is there to show us a different condition, and we'll talk about both of those. At the bottom here, you're looking at the state of the sodium channels across time. So these are the sodium channels that are sitting in the membrane of that neuron, and we're seeing them in different states. When the channels are open, when they're open, it means that the tunnel is open. The channel itself, the passageway, is open, and sodium ions can pass through. When the channel is closed, it means that the tunnel is closed. The gate has essentially snapped shut, and you can see it's actually located right in the middle of the channel. Now there's a third state shown for these sodium channels, and that's a state called inactivated. In addition to there being a gate that closes in the middle of the channel, there's also a piece of the protein that sort of hangs down underneath the channel. And again, at certain voltages, this hanging down portion that we call the inactivation particle, this portion can actually change shape and swing over and inactivate the channel. So there are really 3 states that a channel can have. It can be open, sodium ions can flow through readily. It can be closed, sodium ions cannot flow through. And it can be inactivated, sodium ions cannot flow through. So the only thing we need to learn more is what's the difference between being closed and being inactivated. And we'll talk about that in just a moment. Starting up at the top, what we're seeing with the pink line is a stimulus, a stimulating electrical signal being received by this neuron. So this would be over at the end where the dendrites are. Remember, this is incoming information. So this is sensory information. Now, you'll notice that what the stimulus does is it goes up, up, up in millivoltage, and then it comes right back down. It's a stimulus. It doesn't last. So even though we don't see voltages listed on the y-axis here, we know that what a stimulus does is it causes the millivoltage of the membrane to go up, to become less negative, and then come right back down. Now let's take a look at the neuron itself and what's happening in the membrane. Here is, again, the range of millivoltage. And you can see the pink line begins at about minus 60. So we're sitting at minus 60 across time. Time is passing by. We're staying at minus 60 because this neuron is at rest. Now, up at the dendrites, the stimulus gets applied. What happens is the membrane potential becomes suddenly a little bit less negative. It goes up, 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 until it hits a critical point that we call the threshold potential. And then what happens at that threshold is the sodium channels open up. At rest, the sodium channels are closed. At minus 60 millivolts, the sodium channels are closed. When the stimulus is applied, and the membrane potential starts to go up, it starts to become less negative. the sodium channels are going to open when it hits a particular threshold voltage. Now what happens? Well, sodium rushes into the cell. The sodium is bringing positive charge with it. So the inside of the cell that was relatively more negative than the outside at rest is becoming less and less and less negative. See that? It's going up, 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 up. It's becoming less negative, more positive, until it hits this peak. This is the second key voltage. The threshold voltage opened the channels, and now there's going to be another voltage up at this peak, which is up in the positive range, and that's going to cause the channels not only to close, but to inactivate. And again, we'll talk about what that means in just a minute. Now this peak voltage up here, this is a critical one, because not only do the sodium channels close and inactivate here, but the potassium channels open. Remember, potassium is going to flow out of the cell, and it's going to take its positive charge with it. So now the membrane potential is going to start to go down, more negative, less positive across time. Now, the green line right here represents the state in the neuron when the stimulus is applied. So we go up, 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 but we don't quite hit that special threshold, that threshold potential. And instead, what happens is the whole thing sort of fizzles out. We go right back down to resting. We have to hit this first key threshold voltage, this threshold potential, for the sodium channels to open. If we don't, nothing really happens. If we do hit it, this happens. And this pink line, this tracing that you would get on a voltage meter, this is what we call an action potential. So to generate an action potential, the stimulus that comes in to a neuron, that sensory information that comes in to a neuron, has to be large. It has to be about plus 20 millivolts. That will be enough to hit threshold potential. So let's think about this. If the membrane is sitting at minus 60 at rest, and we apply plus 20 in a stimulus, that's going to bring us up to about minus 40. We're going to go from minus 60 to minus 40 when a threshold potential stimulus is applied. As long as we hit that minus 40 point, and again, these are approximate millivoltages. As long as we hit that minus 40 mark, we're at threshold. And the sodium channels are going to open. At rest, we're at minus 60. Sodium channels are closed, potassium channels are closed. We stay at minus 60. When the stimulus gets applied, we go from resting membrane potential at minus 60 to the threshold potential of minus 40. At threshold potential, sodium channels open, depolarization occurs. Sodium channels open, sodium rushes into the cell. The inside of the cell suddenly becomes much more positive, much less negative. That's what we call depolarization. So we're going to rise rapidly from minus 40, that's the threshold, to plus 40, that's that peak. Now, plus 40 is our other really critical moment, because at plus 40, the sodium channels are going to close and inactivate. The potassium channels are going to open. Potassium is going to rush out of the cell. So the cell is going to suddenly become much more negative. So we're going to suddenly go from plus 40 back down, 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 down. We're going to go all the way back to resting and beyond resting. Now I'm going to introduce a new term here, and that's this term repolarization. Remember, I said a moment ago that when the inside of the cell suddenly becomes more negative, we call that hyperpolarization. But that's only when you start from rest. So if I begin at minus 60, resting, and I become more negative, that's hyperpolarization. But when I'm starting above resting, when I'm starting at plus 40, and I'm going down to minus 60 to rest, we call that repolarization. We depolarize to plus 40, and then we repolarize to minus 60. Now, what's going to happen in the neuron is when we get back down to resting, we're going to keep going. We're going to keep going more negative than that. It's what we call an overshoot, or some people call it an undershoot. It depends on your perspective. We're going to go from minus 60 all the way down to about minus 75. That is hyperpolarization. And the reason that happens is because the potassium channels that opened up at plus 40, they're going to stay open until minus 75 is reached. So we're going to see a repolarization and then a hyperpolarization to minus 75. So here are the terms that we use to describe the phases of the action potential. We apply the stimulus, and as long as the stimulus brings us to that threshold, we're going to see a depolarization. Then we're going to see a repolarization. Then we're going to see a hyperpolarization. And then we're going to go back to resting. Now, I said a minute ago that the potassium channels are going to close at minus 75 millivolts. So how do we get back to minus 60? Well, remember ion leakage. The ions are going to leak through their ion channels, and that's going to passively bring us back up to minus 60. And then, of course, our old friend, the sodium-potassium ATPase pump, is going to keep us at minus 60, unless and until another stimulus is received. So on the graph, resting potential, stimulus to threshold. If we get up to minus 40, we're at threshold potential. Sodium channels open, depolarization. We hit a peak of plus 40. Sodium channels close and inactivate. Potassium channels open. Repolarization down to minus 60, and then hyperpolarization down to minus 75. You can't see it on this graph, but this pink line would go below minus 60 and then back up to resting at minus 60. Potassium channels close at minus 75. Passive leakage of ions brings us back up to resting potential. Now let's talk for a minute about this strange condition called inactivation of an ion channel. There are what we call refractory periods during an action potential. There are two refractory periods. And what we mean by this word refractory is that the neuron is going to be resistant to another action potential being generated. So during an action potential, it's not easy to start another action potential. There are times when it's impossible to start another action potential, And then there's another time when you can do it, but you need an extra large stimulus to achieve it. So the absolute refractory period is the time when no amount of additional stimulus could begin another action potential. And the reason for this is because the sodium channels are closed and inactivated during this time. That inactivation particle is different from the gate inside the channel. All of the sodium channels are going to open at one voltage and close at another voltage. They're all going to do it together. They're going to open at minus 40. They're going to snap closed at plus 40. The inactivation particle is different. The inactivation particle is going to close the channel at plus 40, but there is no specific voltage that causes that particle to open back up again. Now, you'll understand that a little more clearly when we talk about the relative refractory period. The relative refractory period is the time when only an extra large stimulus is going to generate another action potential. Why? Well, because the sodium channels are going to reactivate one at a time. So during the relative refractory period, any of the sodium channels that have reactivated will be able to generate another action potential. It's just that you're going to need an extra large stimulus to do that. Some of the sodium channels will still be inactivated and they won't respond even to an extra large stimulus. So it's difficult or even impossible at times to cause another action potential to occur in a neuron while an action potential is happening. When we go back to the graph here, the absolute refractory period is going to begin at this peak and go for a little while. I'll show you this more clearly in a moment. And then as the potassium channels are allowing the voltage to go down, 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 more and more negative, you'll come to a point where the relative refractory period begins. So you have from the peak absolute refractory period and then relative refractory period. This graph shows that a little more clearly. On this graph, we're still looking at action potential. We're looking at time in milliseconds. We're looking at voltage. We're also looking at, over here, a diagram of the two important ion channels, the sodium channel in pink and the potassium channel in purple. Up at the top, the other additional information that we have is it shows us where the stimulus is being applied, or I should say when the stimulus is being applied in dark purple. Then we can see the time of the absolute refractory period and the time of the relative refractory period. So at the very beginning of all of this, we have a neuron at rest at minus 60 millivolts, holding steady. There are some ions leaking through the channels here, but that's okay because the sodium-potassium ATPase pump is pumping those ions right back, maintaining the ion gradients. At rest, both of our ion channels are closed. The sodium channel is closed, the potassium channel is closed. Now, we're going to get to this point, we're going to apply a stimulus. Remember, the stimulus is a positive amount of millivoltage. So we're going to go less negative here, up, 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 until we hit that key moment threshold, what we call the threshold potential. At minus 40, sodium channels are going to open. And that's what they're showing us on this slide. Sodium channels snap open. the gate inside the channel is going to change shape. When the voltage hits -40, sodium is going to rush into the cell, and we're going to get a very quick increase in voltage, much, much less negative, more positive, until we hit this peak. At the peak, sodium channels are going to close and inactivate. That's what the little lock symbolizes. The potassium channels are going to open. Potassium is going to flow out of the cell. We're going to see the millivoltage become much more negative now. It's going to go down, down, down. This is repolarization, back to resting. But notice it doesn't stop at resting because the potassium channels are still open. So we're going to keep becoming more and more negative until we hit -75. Then the potassium channels are going to close. Once the potassium channels are closed, what brings us back up to resting is the passive leakage of ions. Once we get back to -60, we will stay at -60 because of the sodium-potassium pump. During the absolute refractory period, the sodium channels are closed and inactivated. No amount of stimulus could begin another action potential during that time period. The sodium channels are starting to reactivate, but they're reactivating one at a time. So during the relative refractory period, you could begin another action potential here, but you would need an extra large stimulus to do that.